Hi, this video is around the measurement of chili powders, specifically the statistics of measuring chili powders. So what I'm going to do is I'm going to just list out the aims and also some of the topics of discussion. One of the topics of discussion will definitely be the intrinsic heterogeneity of chili powder samples. So a lot of analytical sciences, for example, are around pharmaceutical ingredients. There you can expect a greater sort of homogeneity of samples. Maybe doing medical diagnostics in blood, and there's a greater homogeneity. But when you start hitting things like natural products, where we're talking about a chili that's blended, maybe desiccated, chopped up, there can be quite an assortment of particles and parts within that. So I'll discuss the heterogeneity of chili powder. I'll also talk about the averaging of test results. So if you want to get a sort of, let's say, an accurate global perspective on how hot a chili powder is, you might make several tests and you might average them out. I'll talk about the standard deviation of test results. So if you make something like five tests on a chili powder, standard deviation would sort of answer the question, well, what's the kind of range of results that you're getting? And I'll talk about the equation behind it. I'll run an equation and also say, how easy it is to actually just do that really in Excel. I'll talk about relative standard deviation. This is really the topic I want to get to, because when you're doing any kind of analytical science, you've always got you've got kind of three main parts. You've got the sample, you've got the person doing the operation, and you've got the equipment itself. These three things, their interaction between those three things leads to the relative standard deviation. So if you've got a super high relative standard deviation, then you don't have a good repeatability in test. If you've got a low standard deviation, then you have a relative standard deviation rather, then you've got a good repeatability in test, but I'll also get to that. And I'll also discuss rejection of outliers. And if you've got an outlier, how to reject the data point by looking at the standard deviation, looking at its, let's say, value versus the average value plus or minus 3 standard deviations. So I'll also talk about how to reject outliers as well. So first of all, with chilies, there's a lot of heterogeneity in that sample. So what I mean by that is, if you've got something like a chili pepper, chili peppers are very heterogeneous. If you kind of sample them in one part of the chili, you might hit a capsaicin molecule. If you sample them in another part of the chili, you may hit a capsaicin molecule, you may miss it. If you sample here, you do hit the capsaicin molecule. And if you sample it here, then you definitely do hit 2 capsaicin molecules. Now, when you get to chili powders, they've been blended, maybe dried, and you've got something that's more homogeneous, but not necessarily 100% homogeneous. So if I sample here, I get a capsaicin. If I sample here, I get 3. If I sample here, I get 2. If I sample here, I get 3. So there's a certain amount of heterogeneity in this sort of image of a capsaicin, of a chili powder here. Here I'm talking about a chili sauce. So if I sample here, I get 12. If I sample here, I approximately get 12. So the more homogeneous a sample is, like a chili sauce, then the easier they are to sample, and the much lower the relative standard deviation. So when we talk about relative standard deviations, the relative standard deviation for a sample type can come both from the test but also from the sample itself. So chilies are kind of very heterogeneous. Chili powders are sort of not as heterogeneous, I'd say, as a chili pepper, but definitely not as homogeneous as a chili sauce. So the highly heterogeneous, homogeneous, and then the chili powder sits in the middle. If I did, and I haven't really introduced relative standard deviation yet, but if I was to sort of do a back the envelope calculation on a chili pepper, I could actually end up with a relative standard deviation of 141%. On a chili powder, I mean, these are just back of the envelope calculations, I could end up with 43%. And with a something like a Tabasco sauce, which is very blended, very homogeneous when you actually look at it, you could end up with a relative standard deviation of 13%. If you do look at a chili a chili powder underneath a microscope, and these are microscopic images that I have taken in this office, then you will find out that actually they're full of particulates that are at least different color, and different sizes. So it is a heterogeneous sample. Um, Now, understanding that the sample is heterogeneous, if you really want to do a sort of accurate measurement of a chili powder, it's not good enough to take one sample, one test, and you're done. You actually end up having to sample and test in several places, so you can get a sort of understanding of the heterogeneity of that sample, of that powder rather. Now, that means that, strictly speaking, for example, an objective way of trying to do it is to take 5 samples, send them off to an HPLC lab. You may get a turnaround in 1 week. It possibly costs you $100 per sample. It's just not particularly kind of economic or even possible, I would say, with the kind of margins that are necessarily involved with chilies. So HPLC, expensive, and people only do one test. Just because of that, we've obviously got the food sense, so we can actually do a lot more testing in a lot less time. I am going to introduce the terms average, which most people obviously understand, the standard deviation and relative standard deviation, which might be new terms to people. And I'll also talk about outlier rejection as well. So in this one, this is data not gathered by ZP, but gathered by one of our clients. They're in India. They routinely test chili powders. I'm not sure if it's what it calls incoming quality control or outgoing quality control. But you can see their food sense Gen 4 there. They've made up their powder suspensions here. I can see their vortex are in the background. Bit of a calculator, so obviously do some calculations. And then for each sample they've prepared and tested. So they've ended up with 5 results. I'm going to start using their results as a way of illustrating mean standard deviation, relative standard deviation now. So when they measured this particular powder, they ended up with something like 5 results. And the first thing you should do is when you look at these results, you think, wow, okay, so sample 1 is 55,697. Okay, but actually sample 4 was 91,936. So that's twice what sample 1 actually was. So that, for some people, depending on your kind of perspective, you could think, oh my goodness, that's twice as high. Now that they do have then 3 more samples, 78,000, 73,000 and 82,000. So what you're looking at here is something that has the feeling of what we call normally distributed. There's 1 low, 1 high, and essentially 3 in the middle. So that kind of, if I was to draw what they call a bell curve, I would kind of have this kind of shape where it all peaked in the middle and then had these 2 tails. So you have a low end tail, a high end tail, and 3 making up the results in the middle. So it looks like it's normally distributed. But that said, at a first glance of this, you can see one result's 55,000, another result's 91,000. But what is the global hotness of this powder? And the global hotness of this is just take the average of it, which in this case, add them all up, divide by 5 because there's 5 samples, it's 76,532. Okay. Now, what I'm also adding here then is a kind of a metric of reproducibility, which is plus or minus 18%. And that plus or minus 18% is plus or minus relative standard deviation, but I haven't defined relative standard deviation. But what it means is, if somebody was to ask you, what's the hotness of this powder, you would say 76,532 Scoville units, and I have a certainty of plus or minus 18%. And for them, that's actually quite acceptable because they understand the sort of heterogeneity of actually what they're trying to measure. Now, I'm going to now start to talk about this 18%, this plus or minus 18%, this relative standard deviation. The relative standard deviation comes from standard deviation divided by mean, or I think in more layman terms, average. So standard deviation divided by average times by 100 is the relative standard deviation. So the mean, most people intuitively understand this. If I've got 5 samples, add up the value for the whole 5, divide by 5, and you'll get the average. The standard deviation is less intuitive, and so I will spend the next slide explaining where standard deviation comes from. I will also say that there's an Excel function for this, so you don't have to understand the equation, but if I go through the equation once in a manual way, follow it along embed it, and then because then it'll help to sort of increase understanding later on when we're talking about relative standard deviations with real samples. So let me go forward a little bit and say that, you know, for the mean, it's quite straightforward. Just add up all the values, divide by the total number of values or samples here, which is 5, and I end up with a average of 76,532 Scoville heat units. But then you want to ask the question, well, how repeatable was that, or how consistent, depending on your not your language, but the kind of terminology that you like to use, you know. But what kind of confidence can I have in this? So now we start to come to the standard deviation part. In standard deviation, the first thing that happens is it asks the question, what are the values that you're going to be using? And the values were those 5 tests: 55,000, 78, 73, 91, and 82,000 Scoville heat units. The next question that the standard deviation question, or equation rather, asks is, what's the difference between that measured value and the average value for the population? I think the average was 76,532. So you have to take that value from each one of these values. So that's why 55,000 becomes minus 20,000. 78,000 becomes 2,000. 73,000 becomes minus 2,600. 91,000 becomes 15,403. So these are the differences between the measured value and the average for all of those samples. You don't want, and the next part then is this squared term. So everything is actually squared at that point. So the next column is basically the middle column. So the difference from mean is then squared. This is basically a way of getting everything from being a negative into a positive. So if the difference happens to be negative, it ends up being positive. If it's positive, it remains positive. So everything has become now positive because we squared it. Then the next part of the equation is there's a sort of symbol here which means the sum of. So I have to sum all the square of the differences. So we essentially add up all of this column, and I end up with a sum of the square of the differences. And then we divide by, because I have 5 samples, we end up dividing by 4. So 5 minus 1 is 4. If this was consisted of 6 samples, we would have done it 6 minus 1 is 5. By the way, you don't have to be manually doing it the way I'm doing it. I'm only manually doing it as one illustration. There is an equation, there's a function in Excel called STDEV, standard deviation, and that will essentially do it for you. I'm only doing it manually to kind of be pedantic and make sure that, you know, we at least went through it manually once. So we take the sum here, we divide by 4, we get essentially a new value, and then we do the square root of that, and that brings us to 13,395. So what I can say here is the global average value for this chili was 78,000 plus or minus about 13,000 Scoville heat units, but that's still not very intuitive. So in fact, what you then do is you take, to get to relative standard deviation, you take the 13,000, divided by the, I think it was 76,000, and you will have the relative standard deviation at that point. So let's just do that again. So we've got our list of values. What's the global hotness of it? It wasn't 78, it was 76,532. Okay, so it's just the average. What was the standard deviation? It was 13,395. So therefore the relative standard deviation was standard deviation divided by average times by 100 to get it into percentage, and we have 18%. As I say, there are, and I know many of you watching this will know that there's obviously a function in Excel called average, and there's also a function in Excel called standard stdev, and there's also, you don't need this by the way, this is square roots, but there's also a function in Excel called square root. But because you won't be manually doing it the way I was doing it, you can just use the average and the standard deviation functions. You don't need that square root function. But let me give you an example of, this is a chili powder. It's available for purchase on the internet, and it advertises itself as 1 million, between 1 million and 1,350,000 Scoville heat units. I just want to kind of look at what kind of values or standard deviations or relative standard deviations are behind this. So effectively, if that's what they say the kind of range is, then I'm essentially sort of reverse engineering this. But for example, they would have done a test and they would have scored, in one of the tests they would have got it at 1 million. In another test they might have got it at 1,175,000. In another test they may have scored it at 1,350,000 Scoville heat units. Clearly I wasn't there in the lab when they did this, but these were the kind of numbers that would get them to the range that they're otherwise advertising. So if I do an average of that, the actual average is 1,175,000 Scoville heat units. If I did a standard deviation and then calculated the relative standard deviation, then they actually get to about 15%. Obviously, I wasn't in the lab there, but I'm saying if they can have that kind of range, then maybe when they were actually doing their testing, then they would have actually had an RSD of about 15%. I'm going to talk about outlier rejection at this point. So this is some data. This is essentially real data of a mild looking, not mild, sorry, I say moderate heat chili. Well, let me go through it. So this is 7 tests done on the same chili powder. Test number 1 comes in at less than 500,000. Test number 2 also comes in at less than 500,000. Test number 3 comes in just over 500,000. There's an obviously glaringly obvious test here, which comes in at 2.1 million. And it's just glaringly obvious. And then we got another one here, which is 500,000, another one that's less than 500,000, and another one that's just over 500,000. So these 7 tests are all done on the same powder, and you can see that there's a distinct difference. That I would describe 6 of these tests as being within the same ballpark of each other, and the 7th one being completely off the scale relative to the other 7. So I'm going to show you how you would start developing a criteria to say it's a ridiculous result. I don't know where it came from. It's but can I actually reject it? So I would describe test number 4 as an outlier. An outlier really is a term in statistics. It's recognized to kind of say, I've got a population of data. One of them is extremely different. I describe it as an outlier, but can I actually reject it? Just to say that the average for this particular, let's say chili, based on the 7 results with chili powder, was about 69,000, sorry, not 69,000, 698,804 Scoville heat units. Its standard deviation was about 645,000 Scoville heat units. So therefore, the relative standard deviation is kind of, I want to say off the scale, but it's 92%. It's really very very variable, and it's really all skewed by this particular guy in the middle. Test number 4. Can we reject number 4? Well, there's one way of rejecting outliers, and that's to say, calculate the mean and standard deviation of your data. So we've already run through an example of calculating the mean and standard deviation of data. Then you can determine the range of what you're expecting, and this is what you do is you have the average value, and to determine the upper range you add plus 3 standard deviations, and to determine the lower range you have the average minus 3 standard deviations. I'll do some sort of maths on that so you can actually see what I mean by that. And any point then that falls outside of that range is considered an outlier. Now you can soften up this criteria by actually using either average plus 2 standard deviations or average plus 1 standard deviation. So I would say that sometimes when you add a criteria like, well, I'm not going to reject anything unless it's outside of the range average plus or minus 3 standard deviations, that's applicable in industries like the pharmaceutical industry, where the impact of getting something wrong could be quite could be significant to human health. Also possibly the same in diagnostics as well, where if you were going to make a dose somebody with a certain drug based on a certain value, you want to make sure you get it right. Now in this sort of food industry, where sometimes the risk of calling it wrong on occasions is not so great, you could soften that up a little bit. But I'm going to run it like we are running it in the pharmaceutical industry. So we're going to run outlier rejection based on this plus or minus 3 standard deviations from the average. So let's go back to our example. So we have these 7 results with one that's quite extreme. The average for this population is 698,000. The standard deviation for this, I say population, of these samples is 645,000. The relative standard deviation is obviously high. 3 standard deviations here is just the standard deviation 645,000 times by 3 which brings us to about 1,937,000 standard deviations. So if I want to reject this 2.1 million standard deviation up here, sorry, not standard deviations, 2.1 million result up here, if I calculate average plus 3 standard deviations, I get 2.6 million Scoville heat units. So strictly speaking, I cannot reject that outlier. Now I could soften up my my rejection of criteria by actually calling that 2 standard deviations, and then you would have a sort of softer criterion in to call that. You may soften it up in an industry where actually margins are a bit lower and you can't really afford the kind of to be acting like you're in the pharmaceutical industry, then you possibly could soften that up a little bit. But let's say I'm not going to soften it up. But what you can do is, for example, now what I've done here is I've not gone back into the lab and done testing. So just understand this is essentially a simulation. I've kept the original data, but I've added some more data points. But sort of with the idea that I went into the lab, I really wasn't sure about this 2.1 million. So I thought I'll get more data, I'll pool all of this data together and see what happens. So I've essentially gone back into the lab, I've collected 4 more data points. And they all happen to come in around the 500,000. At that point now, the average for everything is come down slightly. The standard deviations come down because it's all been pulled down because I've got 4 more data points that are kind of approximately 500,000. The relative standard deviation is still terrible. But now if I put my strict criteria onto this and say, okay, I won't reject you unless you are... this is the 2.1 million score, unless you are greater than average plus 3 standard deviations. Well, it's very close, admittedly, but average plus 3 standard deviations here is 2.09. The one here is 2.1, so it just happened to actually get over there. So I could, at this point, if I had gone back into the lab, collected more data, the data came out the way that I've simulated it, at this point I actually could reject the outlier. Because as soon as I reject that outlier then, at this point now, this is the same data, but with the outlier rejected, everything is under 600,000. You can see the sort of distribution here. And now if I do the calculations, actually the average was 445,000 Scoville heat units. The relative standard deviation is 25%. And I should have mentioned actually that you can have relative standard deviations of 25%. 25% is something that is some of the tests that kind of FDA cleared are sort of 25%. So the lower this number is, the better it is. But 25%, 20%, these are good sort of values if you can get under there. And you could see that we could kind of get under there by actually doing more testing to give us more certainty, then doing that outlier rejection, and now the relative standard deviation is 25%. So in summary, food sense is fairly rapid. It's quite good because it actually allows you to collect data much faster and a lot more data to give you certainty over HPLC. We do have to deal with the intrinsic heterogeneity of chili powder. It's not the same as trying to do blood or urine or a pharmaceuticals in industries where actually everything is much more controlled, or in the human body things are much more controlled as well. We can get the global hotness by just doing averaging. You can calculate the standard deviation, and then you can kind of look at, is my repeatability of test acceptable? So for example, I used data from India. That was data gathered for us by a third party, and that was kind of 18%. And then you can actually also use this idea of if data is outside of average plus or minus 3 standard deviations, then you can reject it. But I would also suggest that you can soften it up and say, right, if data is outside of average plus or minus 2 standard deviations, then you can start to reject outliers as well. As always, if you've got any questions, specifically around the testing of chili powders, don't hesitate to contact us at ZP. Okay, thanks very much.